Okay, I have some good news for you. The good news is that we've reached the final chapter of our biochemistry review, purine and pyrimidine metabolism. Some of the most dreaded biochemistry of all medical students. Okay, let's break it down to its most essential parts, and we're only going to hit the points that the boards want you to know. Okay, the first thing we're going to look at is nucleotide synthesis. There's salvage pathways by which nucleotides are pretty much recycled. Okay, you have a good recycling program going on for nucleotides. And then there's a pathway by which we can make the nucleotides from scratch if we need to. We call that the de novo pathway. Okay, let's look at our slide. And on our slide, we see that via the hexose monophosphate shunt, remember the stepchild of the glycolytic pathway, the ribose 5-phosphate could be produced. There were two things produced in that pathway, NADPH and ribose 5-phosphate. Now, the ribose 5-phosphate that gets produced in the hexose monophosphate shunt is going to be the starting point for synthesizing your pyrimidines and your purines. So, the ribose 5-phosphate, it gets converted to an intermediate here that's called phosphoribosyl pyrophosphate. That's called PRPP for short, phosphoribosyl pyrophosphate. So this is basically the ribose 5-phosphate that's been activated by having a pyrophosphate moiety added to it. This is then going to be used for the de novo synthesis of your pyrimidines, necessary for the nucleotide synthesis in DNA and RNA. But also, phosphoribosyl pyrophosphate is an important starting point from nucleotides that are going to be recycled. So purines and pyrimidines can also enter into this pathway via a salvage pathway. So the idea is that there's a salvage pathway and a de novo synthesis pathway that can lead to nucleotide synthesis. Most of the problems we're going to see is in the purine salvage pathway. That's going to be the really important one to remember. All right, we'll start out with pyrimidine synthesis. In pyrimidine synthesis, you have a similar situation to what we saw for the urea cycle. Okay, you have a carbon dioxide molecule coming together with a glutamine. There's a molecule generated called carbamyl phosphate. Does it sound familiar? Well, it should. But the key difference here, there's two key differences. Number one is that this is happening out in the cytoplasm. The first step of the urea cycle, remember, happened within the mitochondrial matrix. The second key point is that the enzyme that's involved here is called carbamyl phosphate synthetase 2. Okay, carbamyl phosphate synthetase 2. Whereas for the urea cycle, it was carbamyl phosphate synthetase 1. Why is that important? It's important, first of all, the goal of this entire pathway is to make DNA. Let's not forget that. So why is this first point I mentioned important? It's important for ornithine transcarbamylase deficiency. In ornithine transcarbamylase deficiency, remember, you had an accumulation of carbamyl phosphate within the mitochondria, and that carbamyl phosphate could leak out of the mitochondria, and it now becomes a substrate for pyrimidine synthesis. So what ends up going on is that your body is going to accumulate orotic acid, and it's actually going to accumulate uracil intermediates. So that's why for ornithine transcarbamylase deficiency, we see orotic aciduria and you see increases in uracil. We didn't see that for, remember, carbamyl phosphate synthetase deficiency. So other than the fact that orotic acid is within this pathway, I wouldn't worry about any of these intermediate steps. What I would worry about is this enzyme called ribonucleotide reductase. Ribonucleotide reductase is what takes a ribonucleotide and converts it to a deoxyribonucleotide. So ribonucleotide reductase is what removes that hydroxyl group from the 2' carbon of the ribose sugar. It gets us from being something that can go into to something that can be going into RNA to something that can go into DNA. Why is this important? It's because hydroxyurea is a drug. Hydroxyurea can block ribonucleotide reductase. Okay, that's a drug that's used to treat, of course, cancer and certain dermatologic conditions, so hydroxyurea. The next enzyme in this pathway, thymidylate synthase. Thymidylate synthase takes DUMP, right? DUMP, deoxyuridine monophosphate, or DUMP, DUMP, and converts it to deoxythymidine monophosphate, or DTMP. So if you remember, U's are found in RNA, T's are found in DNA. So this enzyme thymidylate synthase has a net effect of converting U's to T's. Very, very important for DNA synthesis. What's the drug that blocks this? Well, it's the student's favorite drug. It's 5-FU, 5-fluorouracil, right? I won't give you a symbol for it, but 5-FU, or 5-fluorouracil, is the name of the drug that will block thymidylate synthase. Once again, this could be very useful for treating cancer, for certain dermatologic conditions, 5-fluorouracil. Another enzyme that goes kind of in conjunction with thymidylate synthase is dihydrofolate reductase. So dihydrofolate reductase, if you remember, back to the folic acid synthesis pathway, dihydrofolate reductase is necessary for taking dietary folic acid and converting it to the dihydrofolate and then the tetrahydrofolate form. Okay, so these are varying forms of folic acid. This recycling is absolutely necessary for folic acid to work as a cofactor for methyl donor reactions. Remember, folic acid is an important methyl donor. So in order to convert uracil to thymine, remember there was just a little methyl group on thymine that wasn't present on uracil. Okay, that's going to require folic acid. It requires the enzyme thymidylate synthase and the enzyme that we're showing here, dihydrofolate reductase. What's clinically important? Well, it's clinically important that this enzyme activity can be blocked through certain drugs. So methotrexate. Methotrexate, you know that's used as a anti-cancer drug. It's used to treat rheumatoid arthritis. So methotrexate is an important drug, and it blocks dihydrofolate reductase. How does that help? Well, how that helps is, in the case of cancer, is you prevent the synthesis of DNA because the nucleotides aren't going to be there to make the DNA. And in the case of rheumatoid arthritis, you're going to prevent the rapid turnover of your immune cells. Your immune cells that would be attacking your joints. So methotrexate, an important drug. Trimethoprim. Trimethoprim is going to specifically block prokaryotic dihydrofolate reductase, whereas pyrimethamine is going to block protozoal dihydrofolate reductase. So these are going to be useful as antibiotics. Okay, let's take a look at a table that's going to compare these deficiencies with one another, because extremely likely they could give you a patient with rheumatoid arthritis or a cancer patient, say that they're going to be treated with some sort of chemotherapeutic agent, and they want you to know the mechanism behind that particular drug. So that's what this table is comparing. It's comparing the activities and functions of ribonucleotide reductase, thymidylate synthase, and dihydrofolate reductase, and then telling you which drugs can block these enzyme activities. So ribonucleotide reductase, its job is to take all NTPs, nucleotide triphosphates, and reduce them to deoxynucleotide triphosphates. This is necessary for making DNA. What's it blocked by? Hydroxyurea. Thymidylate synthase. Thymidylate synthase is an important enzyme. It's what methylates DUMP, converts it to DTMP, and it requires tetrahydrofolate. Okay, important to remember that this requires tetrahydrofolate. This is going to be blocked by 5-fluorouracil. Finally, dihydrofolate reductase. The job of this enzyme is going to be to convert, not listed here, but to convert folic acid to dihydrofolate and then dihydrofolate to tetrahydrofolate. If you don't have dihydrofolate reductase, you're going to stop DNA synthesis. And why is that? It's because that thymidylate synthase requires the folic acid. It's going to be used in eukaryotes. You're going to inhibit this enzyme activity via methotrexate activity. In protozoans, you're going to use pyrimethamine to inhibit this enzyme activity. And then in bacteria, you're going to use trimethoprim to inhibit this activity. Now that brings up an interesting point, which is illustrated here, and that's cotrimazole therapy. In utilizing cotrimazole therapy, you're basically combining sulfamethoxazole and trimethoprim. So many times for an antibiotic, trimethoprim, sulfamethoxazole will be given in conjunction with one another in one formulation. Now, how would this work? The sulfa drugs, first of all, they're going to block the conversion of para-aminobenzoic acid to folic acid. So they block the conversion of PABA to folic acid. This doesn't cause a problem for us as people because we don't have an ability to make our own folic acid. Remember, we have to get it in through our diet. So the bacteria, they have to take PABA and convert it to folic acid. If sulfamethoxazole therapy is initiated, it's going to block the bacteria from making their own folic acid. And then using this in conjunction with the trimethoprim is going to inhibit dihydrofolate reductase activity. So if you prevent the bacteria from making their own folic acid, and then on top of that, you prevent it from recycling its folic acid to a useful form, it's a very potent way of treating a bacterial infection. So it's commonly used therapy, the cotrimazole therapy. Here's a figure just showing you ribonucleotide reductase, just emphasizing that it's the enzyme that converts all four here of your nucleotide triphosphates into deoxynucleotide triphosphates. Then there's an enzyme called thymidylate synthase. It's necessary for converting DUMP to DTMP. Let's review what drug blocks thymidylate synthase. 5-fluorouracil. And of course, we see that hydroxyurea is going to block specifically ribonucleotide reductase. Let's now move on to purine synthesis. We talked a little bit about pyrimidine synthesis. Let's move on to purine synthesis. We'll see on the figure here that the starting point, once again, ribose 5-phosphate being converted to phosphoribosyl pyrophosphate. The phosphoribosyl pyrophosphate can undergo a couple of steps, very low important steps, and eventually be converted to the molecule inosine monophosphate. From inosine monophosphate, they can either be converted to GMP, guanosine monophosphate, or to AMP, adenosine monophosphate. Remember, pure as gold. The purines are going to be adenine and guanine, so pure as gold. The only other important point to consider here is that tetrahydrofolate is an important carbon donor, right? So tetrahydrofolate is necessary to donate a carbon to build these nucleotides. Other than that, the biochemistry of this pathway is not really important for you to know, but you should know a couple of things. Number one, allopurinol. Allopurinol is going to be a nucleotide that's going to inhibit purine synthesis. It's actually going to inhibit it at a couple places. The first place it's going to inhibit is purine synthesis. Also, you can use mercaptopurine or 6-MP. That will also inhibit purine synthesis. It will inhibit that pathway, so it can be a useful drug. Later on, we're going to see that hypoxanthine is a base. Okay, it's a base. Inosine is actually hypoxanthine that's linked to a ribose sugar. So inosine is hypoxanthine that's linked to a ribose sugar on the way to building a nucleotide. The next slide is perhaps the most important from this section, other than the drugs that block pyrimidine synthesis that we talked about. And this is the purine salvage pathway. The purine salvage pathway is illustrated here. And what you see is that ATP and GTP, other high-energy compounds, DNA and RNA, well, they're eventually going to be broken down, right? Cells are going to be degraded. The DNA is going to get a little bit nicked up, going to have to be recycled or excreted. And that's what this pathway is describing. So AMP and GMP are going to go down two similar but slightly varying roads. Okay, let's not worry about all the details there, but AMP is going to go down its own road, and GMP is going to go down its own road, and eventually they're going to meet up. They're going to see each other another day. Okay, they're going to see each other another day via the enzyme hypoxanthine guanine phosphorybosyl transferase. I think it might be the longest enzyme we've talked about, but it's hypoxanthine guanine phosphorybosyl transferase. Important enzyme. So they're going to meet up. And they're going to, via this enzyme activity, they're going to be recycled. Don't worry about all of the various forms here. That's not important. What is important is when this enzyme's deficient. When this enzyme's deficient, as I've shown you here, it's going to lead to something called Lesch-Nyhan syndrome. Lesch-Nyhan syndrome is a deficiency in hypoxanthine guanine phosphorybosyl transferase. Perhaps one of the most interesting diseases that you would ever encounter. It leads to self-mutilation activity. It's a very devastating disease. You would diagnose this on a patient case presented to you as a child that's presenting with sand-like crystals in their diaper. What are these sand-like crystals? Well, they're going to be uric acid crystals. They're going to be uric acid crystals accumulating in the diaper. It's going to lead to mental retardation, and as I said, this self-mutilation behavior and an early death. So HGPRT, you have to recognize that is deficiency. You have to recognize that as Lesch-Nyhan syndrome. Okay, why is this a problem? Well, think about it. If there's a block in the recycling of hypoxanthine and guanine, if there's a block there, the only other place that these molecules can go is to be converted to xanthine and then finally to uric acid. Now, typically, 90% of these nucleotides are recycled, and only about 10% are going to be excreted. But if there's a block right here, you're going to decrease the salvage pathway, and you're going to increase the excretion pathway. So now you're just going to be spitting out uric acid into the urine. These crystals are going to accumulate, but they're also going to accumulate in other tissues, and not all of it's going to be excreted. Going to cause a problem. There's another disease we can talk about here, one they love to test medical students on, and that's gout. Okay, let's look at gout for a second. Gout is going to cause an excess accumulation of uric acid. So in gout, you're going to get these deposits in your toe, typically in the great toe. And this is you're going to get tophaceous deposits of sodium urate crystals. It's going to cause a lot of pain, a lot of redness, a lot of swelling. Okay, so gout. In order to treat patients that have chronic gout, what drug do we use? You got it. We're going to use allopurinol. Allopurinol is going to inhibit xanthine oxidase. In addition to preventing purine synthesis, allopurinol is going to act like a nucleotide that is going to compete with xanthine for binding to xanthine oxidase. So allopurinol is a competitive inhibitor of xanthine oxidase. It's going to lower the amounts of uric acid. But would you ever use allopurinol to treat an acute gout? Okay, we would use it to treat chronic gout, but do we ever use it to treat acute gout? No, don't want to do it. But what do you think would happen as a result of allopurinol treatments for acute gout? Is it would actually precipitate, it would further exacerbate the gouty attack. Why is that? It's because, allopurinol itself looks a lot like xanthine, and it's going to precipitate this gouty attack. So how does one treat acute gout? What drugs are you going to use? It's typically going to be NSAIDs like indomethacin to inhibit inflammation. It's going to be things like colchicine. Colchicine, what is colchicine going to do? Can you remember the mechanism of action? It's going to inhibit microtubule formation. So by inhibiting microtubule formation, you're basically preventing the macrophages from gobbling up the uric acid crystals. Okay, it's not the crystals themselves that necessarily cause the problem. It's the macrophages that come in and start gobbling up those crystals, initiating an inflammatory response. Therefore, you get the redness, the pain, and the swelling. The calor, rubor, and dolor that you see typically with inflammation. So there's no effect via colchicine treatment. There's no effect on uric acid production. What's another drug that could be used to treat gout? Well, there's several. There's many drugs, but another one I'm thinking about is probenecid. Remember probenecid? What is probenecid going to do? it's going to stimulate the kidneys to start excreting more uric acid. So for probenecid, you're actually stimulating the renal excretion of uric acid. Once again, you're not necessarily preventing uric acid formation, but you're turning up its excretion. Clinically, if a case is presented to you, and it likely will be, that says that that there was inflammation going on in the toe, and you want to know whether it's gout, whether it's pseudo gout, whether it's rheumatoid arthritis, whether it's osteoarthritis. If they say that they extracted some fluid, and the fluid contained needle-shaped and negatively birefringent crystals, okay? Needle-shaped, negatively birefringent crystals, that's going to be gout, okay? That's going to be gout. It's going to be. If the crystals were perhaps weakly birefringent or positively birefringent, and instead of being needle-shaped, they were more rhomboid-shaped, what's that going to be? That's going to be pseudo-gout. So make sure you differentiate between gout and pseudo-gout. Two closely related topics, but they're going to be clinically different. So on the next slide here, we have this point emphasized. We see that in gout, in acute gout, you have negatively birefringent needle-shaped crystals. That's going to cause the neutrophil-mediated inflammation on your toe. You get these tophaceous deposits. It's going to cause a major problem. Also, we see Lesch-Nyhan syndrome. Lesch-Nyhan syndrome, remember that it's an X-linked recessive condition. Okay, it's an X-linked recessive. It's one of those X-linked recessive diseases that you should remember. So who is it going to typically affect? It's typically going to affect mostly men because of its X-linked recessive. You see the mental retardation. You're going to see this as a result of uric acid accumulation throughout the body, particularly in the brain, causing a problem. Could lead to spastic palsies and lots of pain and self-mutilation behavior. Unfortunately, these patients will often die within the first decade of life. Be prepared for gout, I promise you. You might thank me for it one day, but they're going to test it on your exam. So with that, we have come to the end of our road. We've come to the end of our biochemistry review. I hope that you've enjoyed these lectures. I think that if you go through your book and go through these lectures, it will pay dividends for you as far as your biochemistry on the boards and perhaps help you interrelate some of these concepts. The last thing I want to say is I want to wish you the best of luck on your exam. Okay, I really hope it's everything you wanted it to be and that all your hard work and studying pays off for you with a great board score. I've enjoyed my time with you, and please, you know me a little bit now. I don't know you, so if you ever see me somewhere, just come up and say hi and say, you know what? I spent some time with you. Thanks.